Right now, as you watch this video, you believe you exist in 3 dimensions of space. You can move forward and backward, left and right, up and down. This seems like the most fundamental truth of existence, so obvious it barely deserves stating. But what if I told you that multiple independent lines of evidence suggest this is an illusion? What if the 3-dimensional universe you perceive is actually a projection from a 2-dimensional surface, like a hologram emerging from a flat screen? This isn't science fiction. It's called the holographic principle, and it's one of the most rigorously studied theories in modern physics. The evidence comes from black holes, quantum mechanics, string theory, and recent experiments that seem to confirm the impossible. We might be living in a cosmic hologram. What if everything you think you know about the fundamental nature of reality is wrong? What if depth itself, the very 3rd dimension, is an elaborate illusion encoded on a distant boundary? Today we journey through evidence that challenges everything we thought we understood about the structure of existence itself. Prepare yourselves. We begin. In 1974, Stephen Hawking published a paper that would shake the foundations of physics. He had discovered something extraordinary about black holes, something that seemed to violate the most fundamental laws of the universe. According to Hawking's calculations, black holes aren't actually black. They emit radiation, they evaporate, and when they do, they take information with them into oblivion. This might not sound catastrophic, but to physicists, it was the equivalent of discovering that 2 + 2 might sometimes equal 5. Information, you see, cannot be destroyed. This principle is as fundamental to physics as the conservation of energy. Every particle, every interaction, every event in the universe leaves an imprint that persists. The universe keeps perfect records. But Hawking's black holes violated this principle. Matter falls into a black hole, carrying information about its quantum state, its position, momentum, spin, and countless other properties. The black hole evaporates through Hawking radiation, and that information, gone, destroyed, vanished from reality itself. This became known as the black hole information paradox, and it threatened to tear down the pillars of modern physics. Physicists struggled with this paradox for decades. Some suggested the information escaped through the Hawking radiation, but calculations showed this was impossible. The radiation was too random, too thermal. Others proposed that information was stored in a remnant left behind after evaporation, but this created its own problems. Then, in the early 1990s, physicists Gerard de Hooft and Leonard Susskind independently proposed something radical. What if information doesn't fall into a black hole at all? What if it never crosses the event horizon? Here's where it gets strange. According to their idea, information that appears to fall into a black hole is actually encoded on its surface, on the 2-dimensional event horizon. To an outside observer, nothing ever really falls in. Everything that ever approaches a black hole leaves its imprint on the horizon, like a hologram. Think about that for a moment. A black hole is a 3-dimensional sphere of space, but all the information it contains, every star, every planet, every particle that ever fell toward it, is stored on its 2-dimensional surface. The interior, in a sense, doesn't need to exist at all. The surface contains everything. Susskind called this the holographic principle, and the implications extend far beyond black holes. If information can be stored on the surface of a black hole rather than in its volume, what about the rest of the universe? Could the same principle apply? In 1997, theoretical physicist Juan Maldacena published what many consider the most important paper in theoretical physics in decades. Working within string theory, he demonstrated a precise mathematical relationship between a 5-dimensional space and a four-dimensional boundary. The physics in the interior space could be completely described by a theory on the boundary. This wasn't speculation, it was mathematics. Rigorous, checkable, precise. The implications were staggering. If Maldacena was right, our three-dimensional universe might be a projection from information encoded on a two-dimensional cosmic boundary. Everything we see, everything we experience, every atom and every thought, all of it could be holographic, emerging from a lower dimensional surface. The theory was elegant, it was mathematical, it solved the information paradox. But was there any evidence that our actual universe works this way? But the evidence forces us to confront an uncomfortable possibility. What if reality has one less dimension than we've always assumed? The first piece of evidence comes from a simple but profound observation about black holes. In the 1970s, Jacob Bekenstein discovered that the entropy of a black hole, essentially the amount of information it contains, is proportional to the area of its event horizon, not its volume. This is deeply weird. Entropy measures disorder, or information content. For any normal object, entropy scales with volume. A box twice as large can hold twice as much information. But black holes don't follow this rule. Double a black hole's radius, and you quadruple its surface area. The entropy goes up by a factor of 4, not 8, as you'd expect for a three-dimensional object. The Bekenstein-Hawking entropy formula states that a black hole's entropy equals its horizon area divided by 4 times the Planck length squared. The Planck length is about 10 to the negative 35th meters, the smallest meaningful distance in physics. This means the event horizon is tiled with tiny Planck-sized pixels, each storing one bit of information. The black hole behaves like a two-dimensional information storage device. The volume doesn't matter. Only the surface counts. But this represents just one piece of a much larger puzzle. In 1995, physicist Jacob Bekenstein extended his work to propose a universal entropy bound. According to this bound, any region of space has a maximum amount of information it can contain, and that maximum is proportional to the area of the region's boundary, not its volume. Think about a sphere 1 meter in radius. Classical intuition says it could contain infinite information. Just keep dividing it into smaller and smaller regions. But the Bekenstein bound says no. The maximum information content is determined by the sphere's surface area in Planck units. It's about 10 to the 69th power bits for a 1 meter sphere. This isn't specific to black holes. It's a property of space itself. The universe appears to store information holographically, on surfaces rather than in volumes. Our own observable universe has a boundary, the cosmic horizon, roughly 46 billion light-years away in all directions. If the holographic principle applies universally, all the information in our observable universe might be encoded on this distant two-dimensional surface. Everything we see, from atoms to galaxies, would be a three-dimensional projection from that boundary. In 2016, researchers discovered something remarkable about gravitational waves. When two black holes merge and send ripples through spacetime, those waves leave permanent imprints on the structure of space, a phenomenon called gravitational wave memory. Here's the strange part. This memory is holographically encoded. The information about the event doesn't fill the volume of space where it happened. Instead, it's recorded on the boundary of that region, accessible to observers on the surface. The LIGO and Virgo gravitational wave detectors have now observed dozens of black hole mergers. Each event leaves holographic imprints on the fabric of space-time. The universe is keeping records on surfaces, not in volumes. The most remarkable evidence comes from quantum entanglement. When particles become entangled, their quantum states become linked regardless of distance. Measuring one instantly affects the other, even across the universe. In 2006, physicist Shinsei Ryu and Tadashi Takayanagi discovered a deep connection between entanglement and geometry. The amount of entanglement between two regions of space is proportional to the area of the surface dividing them. This is called the Ryu-Takayanagi formula, and it's been verified in numerous theoretical contexts. Entanglement, this quintessentially quantum phenomenon, follows holographic rules. The connections between particles are encoded on surfaces. Even quantum mechanics, the deepest theory we have of reality, exhibits holographic structure. But this represents just one piece of a much larger puzzle, hidden in the mathematics of space-time itself. Maldacena's 1997 breakthrough revealed something extraordinary. He showed that a specific type of universe called anti-de Sitter space, ADS, a universe with negative curvature, like a saddle, has a perfect mathematical equivalence to a theory on its boundary. The interior is described by string theory with gravity in 5 dimensions. The boundary is described by a conformal field theory in 4 dimensions, a quantum theory without gravity. These two descriptions are completely equivalent. They're different languages describing the same reality. This is called the ADS/CFT correspondence, and it's been tested in thousands of calculations. Every prediction in the interior theory matches the corresponding calculation on the boundary, perfectly. Now, our universe isn't anti-de Sitter space. It's expanding, not saddle-shaped, but the mathematical machinery works, the principle holds, and physicists are racing to extend the correspondence to universes more like our own. The most disturbing evidence comes from a thought experiment proposed by Ahmed Al-Mehri, Donald Marolf, Joseph Polchinski, and James Sully in 2012. They discovered that the holographic principle, applied strictly to black holes, leads to a shocking conclusion. The event horizon should be a wall of high-energy particles, a firewall that incinerates anything that crosses it. This contradicts Einstein's equivalence principle, which says that falling into a black hole should feel smooth at the horizon. You shouldn't notice anything special. But the holographic encoding of information on the horizon seems to require a firewall. This paradox remains unsolved, but it tells us something profound. Reality at the deepest level doesn't behave the way we expect. The smooth fabric of space-time we experience might be an emergent illusion, breaking down when we look too closely at horizons. In 2017, physicists at the University of Tokyo and MIT performed a stunning experiment. Using quantum computers, they simulated a toy universe with holographic properties. They created a 2-dimensional quantum system and showed it produced emergent gravity and space-time in one higher dimension. This wasn't our universe, but it demonstrated the principle. A lower-dimensional quantum system can give rise to higher-dimensional space-time with gravity. Dimensions can emerge from information. More recently, in 2023, researchers at Google's Quantum AI Lab performed similar experiments with more sophisticated quantum processors. They created entanglement patterns that precisely matched predictions from holographic theories. The mathematics of emergence was playing out in real quantum systems. Perhaps the most direct evidence could come from an experiment called the Holometer at Fermilab. This device searches for holographic noise, tiny fluctuations in space-time that would appear if the universe has a pixelated structure at the Planck scale. If space is holographic, built from information on a 2-dimensional surface, then at the smallest scales, it should exhibit jitter, like the pixels on a screen. The holometer uses incredibly precise lasers to search for this noise. As of their most recent results, they haven't found it yet, but the experiment has only ruled out certain versions of holographic noise. Other versions remain possible. The search continues. The evidence extends beyond mathematics and theory into the realm of experimental physics. The holographic principle isn't just elegant math, it's making testable predictions about reality. Let's be clear about what we're saying. The holographic principle doesn't claim the universe is literally a hologram in the sense of a projection from a laser. It claims something more subtle and more profound. The three-dimensional space we inhabit emerges from informations encoded on a two-dimensional boundary. The laws of physics in our three-dimensional universe can be completely described by a quantum theory on a two-dimensional surface. The interior and the boundary are two descriptions of the same reality, like two languages that translate perfectly into each other. This forces us to reconsider fundamental assumptions about space itself. We've always assumed that space is fundamental, that points in space exist independently, and physical laws govern what happens at those points. But holography suggests the opposite. Space is emergent. It's derived from something more fundamental, quantum information and entanglement patterns on a lower dimensional surface. In this view, space-time isn't the stage on which physics happens. It's an illusion created by quantum entanglement. When particles are entangled, they create connections, threads of correlation linking distant regions. These threads, woven together in the right pattern, create the perception of space. This idea has been developed extensively by physicists like Mark van Ramsdonk and Leonard Susskind. They've shown mathematically that the connectivity of space-time emerges from entanglement structure. Where entanglement is strong, space appears smooth and connected. Where entanglement breaks down, space itself tears apart. In 2013, Juan Maldacena and Leonard Susskind proposed that quantum entanglement and wormholes are the same thing, two ways of describing the same phenomenon. They called it ER equals EPR, linking Einstein-Rosen bridges, wormholes, with Einstein-Podolsky-Rosen entanglement. The fabric of reality, the space between objects, the distance between here and there, all of it emerges from quantum correlations on a boundary. This isn't fringe physics. Some of the most brilliant minds in theoretical physics work on these ideas daily. Leonard Susskind at Stanford, one of the fathers of string theory, has devoted decades to holography. He calls it the most fundamental insight about quantum gravity we've achieved. Edward Witten at the Institute for Advanced Study, often considered the most accomplished living physicist, has said that understanding holography is crucial to understanding quantum gravity and the nature of space-time. Juan Maldacena, whose ADS/CFT correspondence started this revolution, continues to explore the implications. In recent work, he's shown how time itself might emerge from quantum entanglement. Even Stephen Hawking, before his death in 2018, came to accept holographic solutions to the information paradox he had created. In his final papers, he explored how information escapes from black holes through holographic encoding on the horizon. The consensus is building. Holography isn't just an interesting idea. It's pointing toward something deep and true about reality. The next decade will be crucial. Quantum computers are reaching the complexity needed to simulate holographic universes directly. Google's Sycamore processor, IBM's quantum systems, and specialized quantum simulators are all being used to test holographic predictions. In 2024, researchers used quantum computers to create entanglement patterns that matched predictions from gravitational theories. They demonstrated how space-time geometry emerges from quantum correlations. This isn't our universe, but it proves the concept works. As quantum computers grow more powerful, we'll be able to simulate larger and more realistic holographic universes. We'll test whether the mathematics of emergence actually produces something resembling our reality. We'll see gravity arise from quantum mechanics, We'll watch spacetime being born from information. Recent breakthroughs suggest we might detect holographic signatures in gravitational waves. The next generation of detectors, LISA in space, the Einstein telescope in Europe, Cosmic Explorer in the United States, will observe gravitational waves with unprecedented precision. These instruments will see the gravitational wave memory effect in exquisite detail. They'll detect subtle holographic imprints left by merging black holes. They'll test whether information really is encoded on event horizons the way holography predicts. LISA, scheduled to launch in the 2030s, will be particularly important. It will observe supermassive black hole mergers, events so energetic they warp spacetime across the entire universe. If holography is right, these events should leave specific signatures on the cosmic horizon, signatures that LISA might detect. The holographic principle has profound implications for cosmology. If our universe is holographic, its entire history, from the Big Bang to the present, is encoded on a distant boundary. Cosmologists are exploring whether this could explain mysteries like dark energy, the accelerating expansion of the universe, and the fine-tuning of physical constants. Some versions of holographic cosmology suggest that what we interpret as expansion is actually the growth of entanglement patterns on the boundary. Upcoming telescopes, like the James Webb Space Telescope's successors and next-generation cosmic microwave background experiments, might find holographic signatures in the earliest light from the universe. Tiny fluctuations in the cosmic microwave background could reveal whether our universe has holographic structure at its largest scales. What does it mean for humans to potentially live in a holographic universe? Does it change anything about our daily lives? In practical terms, no. The chair you sit on, the air you breathe, the stars in the sky, all of this remains real and physical. Holography doesn't make the universe less real. It reveals something profound about how reality is structured at its deepest level. But philosophically, conceptually, it transforms everything. It tells us that space, this thing that seems so fundamental, so obvious, is an emergent phenomenon. It's derived from something more basic, quantum information. It means that the distance between objects, the volume of space, the three-dimensional arena in which we live our lives, all of it is, in a sense, illusory. Or rather, it's a particular way of organizing information that appears continuous and three-dimensional to creatures like us, but that could be described equally well as quantum correlations on a distant surface. We live between the fundamental and the emergent, between the boundary and the projection. The most profound implications emerge when we consider what holography tells us about emergence itself. If space can emerge from quantum information, what else might be emergent? Time might be emergent. Several physicists, including Don Page and William Wouters, have proposed that time arises from quantum entanglement and correlations. At the most fundamental level, there might be no time, just timeless quantum information that, when viewed in the right way, creates the illusion of temporal flow. Matter might be emergent. Particles, atoms, molecules, all of it could be patterns in the holographic projection, no more fundamental than the images on a screen. Even consciousness might be an emergent phenomenon, arising from the same information-theoretic principles that create space and time. This is highly speculative, but some researchers are exploring whether subjective experience has holographic structure. The holographic principle has strange connections to the simulation hypothesis, the idea that our universe might be a computer simulation. If reality is fundamentally information encoded on a surface, processed by quantum mechanics, then the line between real and simulated becomes blurred. Some physicists, like James Gates at Brown University, have found error-correcting codes in the equations of supersymmetry, the same codes used in computer science to detect and fix data corruption. This might be coincidence, or it might suggest something deeper about the information-theoretic nature of reality. To be clear, most physicists don't think we live in a computer simulation, but the holographic principle does reveal that reality is more information-like, more code-like than we ever imagined. Here's a disturbing possibility. There might be multiple valid holographic descriptions of the same universe, different boundaries, encoding the same information in different ways, all projecting the same three-dimensional reality. If that's true, which description is real? Are we the projection from a cosmic boundary? Or are we the fundamental system, with some other universe being a projection of us? The mathematics doesn't distinguish. All descriptions are equally valid. Reality might not have a single privileged perspective. There might be no ultimate answer to what is really real. This is called observer complementarity, and it suggests that reality itself might be fundamentally perspective-dependent, not in a relativistic sense, where different observers measure different things, but in a deeper sense where multiple descriptions of the same reality are all equally fundamental. The holographic principle solves some mysteries but creates others. It explains how information escapes black holes. It connects quantum mechanics and gravity. It provides a framework for understanding space-time itself. But it raises deeper questions. Why does reality have holographic structure? Why is information conserved? Why do we perceive three dimensions when the fundamental description might use two? And the deepest question of all, what is information? We use the term freely in physics, but what is it? Is information physical? Or is the physical world made of information? Is information the ultimate substance of reality, more fundamental than matter or energy? These questions remain unanswered. The holographic principle is a door, not a destination. It opens onto a larger mystery, the nature of reality itself. We began this journey with a simple question. What if our three-dimensional universe is a projection from a two-dimensional surface? We've seen evidence from black holes, quantum mechanics, string theory, and experiment. We've explored how space and time might emerge from quantum entanglement. We've considered what it means to live in a holographic cosmos. The picture that emerges is both beautiful and unsettling. Space is not what it seems. The volume of the universe, the distances between objects, the three-dimensional arena of our existence, all of it might be a holographic projection from information encoded on a distant boundary. Current scientific consensus acknowledges that holography is one of the most promising approaches to quantum gravity. It's not proven, but it's supported by rigorous mathematics, and increasingly, by experimental hints. The next decades will be crucial as quantum computers and gravitational wave detectors test holographic predictions with unprecedented precision. But whether holography is ultimately confirmed or not, it's already transformed our understanding. It's shown us that reality is stranger, more subtle, more information-theoretic than we imagined. It's revealed that the most obvious features of existence, space, distance, dimension, might be emergent illusions. We are creatures of the projection, living in the hologram, trying to understand the code that generates us. We are information attempting to comprehend itself. The universe is vast, the mysteries are endless, the journey continues. But perhaps the deepest mystery is this. In a holographic universe, where everything emerges from encoded information on a distant surface, who or what is watching the projection?